Welcome to qnawire.
Okay, in this problem, we are asked to express the RMS velocity, the root mean square velocity of a particle in a gas. You're asked to express it as the square root of 3p over rho, where p is pressure of the gas and rho is the density of the gas. So these are macroscopic variables. So we're basically asked to find this microscopic quantity in terms of macroscopic variables like pressure and density. So we're going to need two different things. First, we can use the traditional expression for the root mean square velocity given to us by kinetic theory, which is square root 3kt over m, where T is the temperature of the gas, m is the mass of each particle in the gas. So these temperatures are macroscopic variable, m is a microscopic variable, we could say. We also know that from the ideal gas law, which is a macroscopic equation, PV is equal to nkt, where big N is the number of particles, T is temperature still, K is the Boltzmann constant as well. So we need to combine these expressions together. First thing we can do is we can say that from the ideal gas law, we can say KT is simply PV over N. Okay. So let's go over here. Let's start with our first expression, this over here. Let's start here. We can replace the KT by this expression involving pressure. That'll get us one step closer. We will be left with 3p times v over big M over n little m. Next thing we can do is we can express, if we have the number of particles in the gas times the mass of the particle in the gas, this would give us the total mass in the gas. So we can express that as big M, total mass of the gas. And we also know that density is simply total mass over total volume. It's just mass per volume. And that's where we get density in the appropriate place. And that's it. That's the main step. So this is a combination of two expressions, a microscopic one and a macroscopic one. You can use that to derive this expression for root mean square velocity in a kinetic gas. And that's it.